So we have a second practical. This is the L2, and in this L2 we are also to confirm Snell's law. This one, it was obviously stated that we are here to confirm the Snell's law. Alright, so we have the incident angle given to you, and then the refracted angle is what you measured, and then you calculate the sine of the incident angle, that is sine of every value you have here: sine 20, sine 30, sine 40, sine 50, sine 60, and sine 70. And then the sine of the refracted angle. The refracted angle is the value you got from the practical. Now listen, there's something you need to know. Told you that the refractive index formula I gave was n as what? Sine I over sine r, right? So your slope will give you the refractive index in this particular one too. However, we need to actually see if our values are correct or not. I doubt if they will be correct. So we have sine I, sine of the incidence. Take the last two values, first and last values, subtract them, divide by the first and last value for this one. So that would be 0.9396 minus 0.3420 divided by 0.7431 minus 0.2249. all right, when you subtract this with your calculator, it's going to give you a particular answer. So we have 0.9396 minus 0.3420 divided by 0.7431 minus 0.2249. What did this give to you? It gave us 1.15, which suggests that this, because the refractive index of glass is supposed to be around 1.6, but I'm going to work with this value. It suggests that these values have comma, but I'm going to work with these values. The reason why I'm doing this is so that when you are doing your practical, you should be expecting your values in such a way that when you divide them, it's supposed to give you us 1.60, 1.5, 1 point something. But if you are getting 1.15, I doubt if you are correct. However, report it the way it is. That is why it is an experiment. Don't try to now forge values to get the correct answer. Experiments are meant to either be correct or wrong. Is that okay? All right, so that is that. Now let's see the question here. Says state Snell's law and draw a suitable graph to deduce the refractive index. Now Snell's law states that the sine of the incident angle to the sine of the refracted angle are constant for a given pair of media. In other words, Snell's law says that n is equals to the sine of the incident angle to the what? The sine of the refracted angle. That's what I just stated. Say the sine of the incident angle to the sine of the refracted angle are constant for a given pair of media. Snell's law, according to your secondary school textbook. I think that is the definition there. That is the definition that is still in my head up till now. You know, we read very well when we were in secondary school. So let's say Snell's law from ChatGPT and see what it gives to us. Snell's law from ChatGPT. Let's see what it gives to us. Say Snell's law. All right. Now it says Snell's law is also known as the law of refraction. Describe how light wave changes direction as they pass from one medium to another with a different refractive index. This law is named after the Dutch scientist Wilbrod Snellius. That's where the name came from, who formulated it in 1621. Snell's law is mathematically expressed as this. I've stated the law to you, so if you want to write all this plenty grammar here, you can decide to write it, but that is not what Snell's law is. Now, these are the key points. Snell's law explains why light bends when it travels from one medium to another with a different refractive index. Have you ever tried putting your gari maker, the turning stick you used to make gari, or a spoon inside, or even a spoon inside pot, and you try looking at the pot, you discover that the spoon is bent inside? This is because of light. You are seeing it from that perspective. It's refracted. Are you getting it now? That is what the Snell's law is actually trying to tell us about. It states that it explains why light bends when it travels from one medium to another with a different refractive index. If light travels from a medium with lower refractive index to a medium with higher refractive index, the refracted ray bends towards the normal. All these ones, they are just English. Alright, so you state the Snell's law. How do you confirm Snell's law? You use this formula. N is equals to sine I all over sine r. So it means we are going to plot a graph of sine I on the y-axis and then plot a graph of sine r on the x-axis. Alright, so that is the graph we are going to plot now. Alright, exactly. Alright, so we are going to plot that graph now, the graph of sine I against sine r. Now, how do we plot the graph? It's very simple. First, we have to draw our line to represent the various axes. So we start with the y-axis, which goes like this. I believe it's going to go higher. And then we have the x-axis, which comes this way. And of course, we are going to write our various 0, 0. Now, the title of the graph. What do you think will be the title of the graph? Now, before we write the title of the graph, let me extend this a little bit higher, because notice the one we did earlier could not contain this space. We had to extend it. So let me take this a little bit higher. So we can say this is a graph of sine I against sine r. Alright, of course you have this axis, sine I axis. The previous practical we did, we not write the various axes. Please endeavor to write it. Alright, I mean the first practical we did here. Why is this one not going up? When there are different touch capability begins to misbehave, then we have sine r. Alright, now which is the x-axis? Then sine I is the y-axis, so we can put y bracket sine I. Now, have we done this? The next thing we need to do now is to choose a suitable scale for our work. Sine I started with 0.3 and ended with 0.9. Alright, okay, your man will be able to carry that. So here you can start with 0.1, so here will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Alright, and then it continues 0.6, yeah, 0.7, 0.8, 0.9, 1.0. This is your y-axis. So you can come here. Now, how about your x-axis? I think x will still follow the same thing. Alright, so you can say let 0.1 represent, or let 2 centimeters rather represent 0.1 units on y-axis. Now let me see your graph. This is your manual here. If the y-axis will be able to take up to that amount, I mean x-axis will be able to take, we will have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. It will be able to take up to 0.7. So for the y-axis, I mean for the x-axis, we say let 1 centimeter, don't use 2 centimeters, represent, alright, 0.1 units on x-axis, because if you use 2 centimeters, it will not be up to. So we can come here, alright, and start putting in our values. So here will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. These are your values will be. Is that okay? These are your values will be at the end of the day. So let's start our plotting. If we want to plot our graph now, alright, so we have the first one is 0.34 and 0.22. So sine I 0.34. So This is 0.3. 0.34 will be close to 0.35. The 0.22 will be just above 0.2, so it will be somewhere around here. This is where the point will fall into. Alright, and then we have 0.5 and 0.32. So we have 0.5, which is here. There's 0.3. This is 0.3. So 0.32 will be somewhere around here. And then we have 0.64 and 0.40. This is 0.4. Then 0.64 will be somewhere, 0.6 rather. 0.64 will be somewhere around here to 0.40. 0.40 is just here, somewhere around here. So the point will be here. And then you have 0.76 and 0.59, which is approximately 0.6. So we have 0.7. If we want to go up, 0.76 above 0.75, and then the other one is 0.6. so if here 0.4, that will be 0.5, here will be our 0.6, which will fall somewhere around here. And then the other one is 0.8660 and 0.63. This 0.866 will be somewhere around here. Then 0.62, or let's say 0.63, will be somewhere around this region. And then the last one, I think the last one is 0.9 and 0.74. So we have 0.99 what? 94 and 0.74. I think this line here, okay, wait to, it's 0.62. 0.62. Did we, okay, I put that one at 0.6. So 0.62 will be somewhere around here. Sorry about that. You know, this is 0.6. So 0.62 will be somewhere around here. To be somewhere around here. But it's 0.8660, so it will be somewhere around here. These person's values are maybe incorrect, but I still want to show you that you can plot any value. Then 0.9 and 0.74. So we have 0.94 and then 0.74. So we have 0.94 somewhere around here. Then 0.7. Here is 0.7. 0.74 will be somewhere around here. Alright, to be somewhere around here. What value is this? 0.6, and this is 0.74, to be somewhere around here. Alright, I believe so. So that will be, yeah, exactly, it's correct. This is our value. So we have to draw the line of best fit. We have to draw the line of best fit. What line actually passes through this value, and in such a way that it can actually cross at least some of these values very well. Okay, let's take this one. Shall we take this one, or we shall take this one? Most of the line did not enter, but that does not discourage you. That is just why I took these values. If not, from the onset I know that there is something wrong with these values, but I just don't want to, because that is how practical it is. Alright, just 2 points can enter, but at least it should be up to 3 points. So what I'm going to do is I'm going to assume that this point entered. Assumption, imagination. Where did the point? Where was the? Okay, somewhere around here. So let's assume that this point entered. That is like 3 points that entered. At least 3 points should enter into your line of best fit. Is that okay? At least 3 points should enter into your line of best fit. they never enter very well, but you cannot say because this is not a good graph. All right, so this is how your graph looks like in this particular one. Now what do you now do? You take your slope. How do you take your slope? I've told you how to take slope before. Now take the first value. Did this value not enter? This particular one here should. God, I beg you. All right, to take your slope, what we'll do is to take this last value. All right, and then take this one. Your slope should be as big as possible. If possible, it should span the entire length of your graph. I don't know why this one don't go hook. All right, so this is your slope. If you trace it down, so we can say our slope, you come here. Now I told you that you are not to write it here. It's changing y over changing s, which is y2 minus y1 all over s2 over s1. What is our y2? Y2 is 0.9. What was the value we got here? 0.94 approximately. So we can take it 0.939, 0.94 approximately, minus what is our y1? Y1 is 0.3420 or 0.34. So we have 0.34. S2, of course, S1 is 0.24, right? 0.224, or let's say 0.22 approximately, minus our S2 0.74. So we have 0.74. Now if you punch this in your calculator, it's going to give you the answer for the slope, which is 0.94 minus 0.34. What would that give to you? 0.6 divided by 0.74 minus 0.22. That will give us 0.52. all right, so we have 0.62 divided by 0.52, which will give us 1.19. so our slope here gave us 1.19, but I told you that the values for your slope are supposed to be hovering around 1.6, 1.5, 1.7, and even 1.8, not as low as 1.19. The refractive index of water is around 1.3. That of glass is higher, around 1.6, because that is what you're actually calculating, refractive index of glass. So your values, you cannot copy this particular one. So I'm very confident that most of you will not go and copy this nonsense into your manual, but follow the procedure. That is what I mean. Like, just understand how to solve it. But this value on 1.19, if you get a value like this, be using corner eye to look at your manual. Although report it the way it is, you don't need to try and start painting your manual and then getting error. So our slope is 1.19. all right, so now having gotten the slope as 1.19, we now come back to our questions. All right, so the other question says state Snell's law. I've stated the Snell's law for you, told you where to get it. You can get it so that the manuals will not all be the same. Just browse the ChatGPT. Snell's law is going to give you. You can go to Google, browse Snell's law, is going to give to you. But I've stated it to you that Snell's law says that the sine of the incidence angle to the sine of the refracted angle are constant for a given pair of media. That is what is your physics textbook, and I can still remember 10 years ago that was what we were stating as Snell's law when we were in secondary school. All right, So that is that. Now the Snell's law, it does not have any unit because you're actually talking about sine I over sine r. Both of them are angles, so degree cancel out each other. No unit for refractive index. And refractive index is very, very important, especially those of you that will come into pharmacy, chemistry, and so on and so forth. It's actually a means for testing the purity and the for checking the authenticity of various drug molecules and other medicinal compounds and other pharmaceuticals. Are you getting in the refractive index? Because the refractive index of one material might be different from another material. So in a situation where they give you two drug molecules and then they say these two drug molecules are the same, and then you carry out refractometry, the process, the general process is called refractometry, and then the instrument they use is called refractometer. You actually carried out refractometry, and then you discover that the refractive index of the two drug molecules given to you, of the two pharmaceutics or medicinal compound given to you, are not the same. Then you know that one of them is either impure, or maybe one is not the drug that we are actually considering at all. So refractive index is very, very important. It's one of the physicochemical parameters that is looked at for when you are characterizing various drug molecules. Is that okay? So for those that you be like, oh, I've seen several people post some this thing and be like, they've not actually known the value of that glass they are looking at. Is because they've not actually advanced in studies and they don't really know the application of that stuff. All right, that's what we are looking at from that glass. Is just like a manual form of the refractometer itself. The refractometer, you just put your whatever, and then that one will give you the various values that you need to get. Now, what are some of the precautions? You say we should deduce the refractive index of the glass. You've deduced the refractive index. The refractive index is the slope of that graph. The slope of that graph is the refractive index. So when they say deduce the refractive index, you say slope, which is also equals to n, is sine I over sine r. Then you put in your values, and then your answer was 1.19 the other time, Abi, which of course I told you that is not even close to the value. The value is 1.6, 1.5, and so on and so forth. So the person that has these values, don't cancel, just write it the way it is. That is why it is practical. Are you getting it? Report it the way it is. Now, list the possible source of errors. What are some possible sources of error? You have parallax error. Is something that we cannot do without when we are talking about physics practical, even when it is not there. Parallax error. All right. Another error that we also have is zero error of meter rule, because you'll be using meter rule for your measurements and for other reasons. So you have zero error of meter rule. Is that okay? These are various sources of error. Zero error of meter rule. Then you have personal error. From the ineptitude of the experimenter. Personal error from the ineptitude. When you talk about ineptitude, you are talking about your skillfulness of the experimenter. These are, and then also random error. Random errors are errors that you cannot really pinpoint that this is what is actually causing it. The environmental condition could cause random error, and so on and so forth. And then systematic error, this method you use for the practical, it might also be a source of error. So I've given you several sources of error. You can copy the one that you think is actually good. And then the next one is compute the standard error in the refractive index. Of course, we said the refractive index is the slope. So if they say compute the standard error in the refractive index, it means they ask us to calculate the standard error in the slope. And standard error, my dear student, from what you know, what is the formula for standard error? Is 4W all over NR. 4W all over NR, which is equals to 4 times, what is our W? I told you that W is our vertical scatter. Now, how do we get the vertical scatter? You get the vertical scatter from the practical itself, which is from the graph rather. That's how you get the vertical scatter. Now, this particular practical, the vertical scatter is quite big. We are going to do it like that. That will tell you the margin of error that is actually present in this particular one. So how do you get the vertical scatter? Look for the farthest point from the midline. on both sides and then rule. If you look at it, these 2 points are not on the line, but this one is farther from the midline. So you are going to take it from here, and then you are going to rule. So we take it from this point like this, and then we rule down. It should be a straight line. Are you getting it? We also take it here, and then you rule up. It must be a straight line. Straighten it if it is not straight. All right, so this is the vertical scatter to this side. Now to this other side, this other point here is our vertical scatter. Is that okay? Now at the end of the day, you will now place your meter rule here and measure the distance from here to here, the distance from the upper line to the lower line. So you place your meter ruler normal to the line. When you say normal, it means I go 90 degrees. Now this my software can actually tell me without using a ruler the vertical scatter. So the vertical scatter here is 1.5 centimeter. That's the vertical scatter, 1.5 centimeter. You don't need to show the line you ruled, just all right. So the vertical scatter here is 1.5, but this is quite high, but I'm going to use it like that. So if we have the vertical scatter as 1.5, so we come here and say 1.5 divided by n is the number of points on your graph. Number of points on your graph, you can easily get it by counting these values here, which is 1, 2, 3, 4, 5, 6. So you have 6 points in the graph. So we have 6 times arrow is the range of value, the horizontal range. What is on the horizontal as a sign arrow? So the horizontal range is the highest value minus the lower value, which is 0.7431 minus 0.2249. all right, so we have 0.7431 minus 0.2249, which gives us 0.51. So we come here and say this is 0.52 approximately. So you multiply 4 times 1.5, this will give you 6, divided by 6 times 0.52 will give us 3.2 for this person. So we say 6 divided by 3.2 will give us 1.87. This is your error, to tell you that there are very obvious error in this practical. Your error is not supposed to be up to 1 point something, 0 point something. Are you getting it now? Now if most lines fall into your vertical scatter, some of you may say, okay, let me put my vertical scatter at 0.5. If you put it at 0.5, 4 times 0.5 will give us what here as 4, as 2 rather, because 2 times 0.5 is 2. So we will now have 2 divided by 3.2, which will now give us 0.65. If you get vertical scatter 0.625, that will be very correct. And the vertical scatter now, what will actually give you your vertical scatter is the how much the how scattered the values are, how scattered your values are. And you know, the more values that enter into your line, the correct your graph, the more correct your graph is, and the more correct your practical results are. So that is that for the standard error. And I think that is all for this particular practical. We'll see you in the next one. Bye bye.